All right, let's go. Number 10. The Great Oxygenation Event. Approximately 2.4 billion years ago, long before continents had taken their current shapes, long before complex cells had organized into anything resembling a body, the atmosphere of Earth began to fill with poison. Not from a volcano, not from an impact, from life itself. A microscopic organism called cyanobacteria, drifting in shallow seas across a planet that had no name and no witnesses, began doing something no living thing had ever done before. It split water molecules using sunlight and released a waste product into the air. That waste product was oxygen. To the organisms that ruled the Earth at that moment, oxygen was a weapon. The anaerobic microbes that had dominated the planet's oceans for over 1 billion years had evolved in a world without it. Their biochemistry was built around methane, sulfur, and iron. Oxygen tore through their cellular machinery the way acid tears through fabric. It oxidized their proteins. It destroyed their membranes. It poisoned the chemistry of life as life had known it. And the cyanobacteria kept producing it. For tens of millions of years, the oxygen they released was absorbed by the oceans themselves. Dissolved iron, abundant in the early seas, bonded with the new gas and precipitated to the seafloor as iron oxide. The oceans turned rust red. Vast bands of banded iron formation, layers of rusted rock that geologists still mine today across Australia, South Africa, and Western Australia's Hamersley Range, were laid down during this period. Entire seas rusted. The continents themselves became stained red as the new atmosphere reached land and oxidized the minerals exposed at the surface. The geological record preserves it as a color change visible across 2 billion years of stone. Then the oceans saturated. The iron was gone. The oxygen had nowhere left to go but up. The atmosphere transformed. The orange methane haze that had wrapped the young Earth in a thick chemical shroud thinned and dissipated. Methane reacts with oxygen. The two gases cannot coexist in significant quantities. As oxygen rose, methane fell, and methane had been the dominant greenhouse gas, keeping the planet warm beneath a sun that was then 25% dimmer than today. The sky shifted from orange to pale blue. The thermostat broke. The Huronian glaciation followed. Temperatures collapsed. Ice sheets advanced from the poles and kept advancing. Some models suggest the glaciers reached the equator itself, encasing the entire planet in a shell of ice that may have persisted, in pulses, for up to 300 million years. A frozen world, a snowball Earth. The longest ice age in the planet's history, triggered not by an asteroid, not by a supervolcano, but by a single-celled organism's metabolic byproduct. The death toll is incalculable because the victims left almost no fossils. They were single cells. Soft, microscopic, ungrounded in the rock record. But the chemistry tells the story. The anaerobic ecosystems that had dominated Earth for over 1 billion years collapsed. Entire branches of the tree of life were pruned back to refugees in deep sediments, hot springs, and oxygen-starved muds where their descendants still hide today. This was Earth's first mass extinction. It was caused by the gas you are breathing right now. What makes the Great Oxygenation event particularly disturbing isn't its violence. It's its mechanism. Life did not destroy itself through war or competition or scarcity. Life destroyed itself by succeeding. The cyanobacteria were doing what evolution had selected them to do. They were thriving. They were efficient. They were spreading. And in doing so, they engineered an atmospheric catastrophe that nearly sterilized the planet and locked it under ice for longer than complex animals have existed. The oxygen never left. The ice eventually retreated. New organisms evolved that could use the poison as fuel, and every breath drawn by every animal that has ever lived is a continuation of that bargain. We are descended from the survivors of a planetary execution carried out by microbes. The atmosphere we depend on was a crime scene before it was a cradle. Number 9. The Late Devonian Anoxic Event. In 1967, paleontologist Digby McLaren stood before the Geological Society of America and proposed something that no one in the room was prepared to accept. The fossil record across the Devonian Carboniferous boundary showed a die-off so severe, so geographically widespread, and so abrupt in geological terms that it could not be explained by gradual environmental change. Something had killed 3/4 of the species alive on Earth approximately 372 million years ago. Not in a single moment. In pulses. Wave after wave of extinction separated by intervals long enough for ecosystems to attempt recovery, and short enough that recovery never completed. The oceans were being murdered slowly, and the murder weapon was something no one had thought to suspect. The killer was a forest. During the preceding 50 million years, plants had been doing something unprecedented in Earth's history. They were learning to stand up. Early vascular plants evolved roots, then woody stems, then the cellular architecture necessary to grow tall. By the late Devonian, the first true forests had spread across the continents. Archaeopteris, a tree reaching 30 meters in height with a trunk a meter thick, colonized landscapes that had been bare rock and lichen for the entire history of the planet. The transformation was extraordinary. It was also catastrophic. Roots break stone. Roots release minerals. Roots pull carbon dioxide from the atmosphere through photosynthesis and lock it into wood and soil at rates the planet had never experienced. As the forests expanded, atmospheric CO2 collapsed. Temperatures dropped, and the newly weathered continents flushed massive quantities of nutrients into the oceans through rivers that hadn't existed in their modern form until plants stabilized their banks. The oceans responded the way any nutrient-flooded body of water responds. They bloomed. Algal mats expanded across continental shelves. The blooms died. Their decomposition consumed, dissolved oxygen at scales the marine ecosystem could not sustain. And then the water turned. What followed is preserved in the geological record as black shale layers found on every continent, deposits so dark and so organic rich they can be lit with a match. The oceans became anoxic. Then they became euxinic, saturated with hydrogen sulfide produced by sulfate-reducing bacteria that flourished in the absence of oxygen. The seas turned inky black and oily. Dead zones spread across entire ocean basins. Coastlines for thousands of kilometers were lined with bloated, decaying fish and the disarticulated remains of reef-building organisms that had defined marine ecosystems for tens of millions of years. The stench of rotten eggs would have carried inland on every onshore wind across every continent simultaneously. The reefs died first. The trilobites that had survived every prior catastrophe of the Paleozoic were reduced to a handful of lineages. The armored placoderms, the largest predators the oceans had ever produced, vanished completely. 3/4 of all species on Earth were erased in a series of extinction pulses, now known as the Kellwasser and Hagenberg events. And then, as if the planet were determined to finish the work, the impacts came. The Siljan Ring in Sweden, a crater 52 kilometers wide, was carved into the Earth during this interval. Additional impact structures of late Devonian age have been identified in Australia and North America. Whether the impacts triggered the extinction pulses or merely accompanied them remains debated. What is not debated is the alignment. The greatest evolutionary innovation in the history of terrestrial life, the rise of forests, occurred precisely as the oceans were being poisoned and the sky was raining stone. What makes the late Devonian particularly disturbing is the mechanism. This extinction was not delivered by an external blow. It was generated by life itself, by the unintended chemistry of success. Plants conquered the continents, and the conquest nearly ended complex life on Earth. the same biosphere that produces our food and our breathable air, has, twice now, demonstrated that it can suffocate itself by becoming too productive too quickly. The forests survived. Almost nothing else did. Number 8. The Siberian traps and the day life almost ended forever. Approximately 252 million years ago, in what is now the frozen wilderness of central Siberia, the Earth's crust split open and began to bleed. Not for a day, not for a century, for nearly 2 million years. The Siberian Traps eruption was not a volcano in any sense a modern human would recognize. It was a continental wound, a network of fissures that vented magma from the Earth's mantle in a sustained geological hemorrhage that has no analog in human experience. By the time the eruption finally ceased, basalt lava had buried an area roughly the size of modern Australia. Layer upon layer of cooled rock now stretches across Siberia, in deposits that in places exceed 2 miles in thickness. Walk across the Putarana Plateau today, and you are walking on the cooled blood of the deep earth, stacked into cliffs that record the slow, methodical murder of a world. In 1992, paleontologist Douglas Irwin at the Smithsonian Institution began publishing a series of papers that would establish the magnitude of what happened next. The geological boundary at 252 million years ago marks the most catastrophic extinction event in the history of life on Earth. Scientists call it the Permian-Triassic extinction. Those who study it call it something else, the Great Dying. The numbers are almost unreadable. 96% of all marine species vanished. 70% of terrestrial vertebrate species were erased. Insects, the most resilient and diverse group of animals ever to exist, suffered the only mass extinction in their entire 400 million year history. Coral reefs that had flourished for hundreds of millions of years disappeared so completely that the planet would not produce reef ecosystems again for nearly 10 million years. Forests collapsed. Soil itself stopped forming properly because the fungal and bacterial networks that produced it had died. But here's where the catastrophe deepens into something genuinely unrecognizable. The eruption itself, vast as it was not what killed most of the planet. What killed the planet was what the eruption released into the atmosphere and the oceans. The Siberian traps did not just produce lava. They burned through enormous coal deposits and carbonate rocks as they erupted, vaporizing carbon that had been locked away for hundreds of millions of years. Trillions of tons of carbon dioxide poured into the atmosphere. Methane followed. The greenhouse effect that resulted didn't warm the planet gradually. It cooked it. Ocean surface temperatures in equatorial regions are estimated to have reached 104 degrees Fahrenheit. The seas became hot baths. Fish that could not flee to deeper, cooler water simply died where they swam. And as the oceans warmed, they lost the ability to hold dissolved oxygen. Vast regions of the world's seas became anoxic, devoid of breathable oxygen entirely. In those dead zones, a different kind of bacteria flourished. Sulfur-metabolizing microbes that thrive in oxygenless water multiplied across millions of square miles of ocean. They turned the seas a sickly, luminous green. They produced hydrogen sulfide, a gas so toxic that even small concentrations are lethal to complex life. The oceans began to exhale poison. The hydrogen sulfide didn't stay in the water. It bubbled up into the atmosphere in concentrations sufficient to kill terrestrial life along coastlines. It degraded the ozone layer, allowing ultraviolet radiation to flood the surface. Plants struggled. Photosynthesis faltered. The base of every food chain on Earth began to crumble simultaneously. What makes the Great Dying particularly terrifying is its duration. This was not an event. It was an epoch of dying. The extinction unfolded in pulses across approximately 60,000 years, with the most severe phase concentrated in a window of perhaps a few thousand. Generation after generation of every species on the planet was born into a world more hostile than the one their parents had known. There was no recovery within memory. There was no return to normal. Normal had been annihilated. Life survived. Barely. The recovery took 10 million years, and the biosphere that eventually re-emerged was fundamentally different from the one the eruption had erased. The Earth did not heal. It became something else. The lava fields are still there, cold now, weathered into stepped plateaus that catch the Siberian sunlight in summer. Beneath them lies the boundary, a thin dark line in the rock that marks the moment the world almost ended for good. Number 7. The Eltanin impact, the only deep ocean asteroid strike in geological history. In 1981, a research vessel called the USNS Eltanin towed a sediment coring rig across the floor of the Bellingshausen Sea, a remote stretch of the Southern Ocean between Antarctica and South America. The cores it pulled from nearly 5,000 meters of black water contained something that had no business being there: iridium, platinum group elements, shocked meteoric debris embedded in marine sediment dated to approximately 2.5 million years ago. The signature was unmistakable. Something from space had struck the deep ocean, and no one had ever found evidence of such an event before. In 1995, geologists Franz Kite and John Wasson at UCLA published the analysis that confirmed it. An asteroid, roughly a kilometer wide, approximately half a mile across, had slammed into water nearly 5 kilometers deep. It remains the only major deep ocean asteroid impact ever identified in the geological record. The mechanics of what happened next defy ordinary catastrophe modeling. When an asteroid strikes land, it excavates a crater and ejects rock. When an asteroid strikes deep water, it does something far stranger. The Eltanin object passed through 5 kilometers of ocean in less than a second, struck the seafloor with a force estimated at over 100,000 megatons, and instantly vaporized a column of seawater reaching from the abyssal plain to the upper atmosphere. A pillar of superheated steam approximately 25 miles tall rose from the impact point. Trillions of tons of ocean water flashed into vapor in seconds, punching a temporary hole in the Southern Ocean that the surrounding sea immediately rushed to fill. The collapse of that hole generated the tsunami. Models published by Stephen Ward at the University of California, Santa Cruz, and Eric Asfog in 2002 estimated wave heights radiating across the entire Pacific Rim. Coastlines from Chile to New Zealand to the western edge of Antarctica were struck by walls of black water exceeding 200 meters in height. That's 650 feet, higher than a 60-story building. Sediment cores from southern Chile and the Antarctic Peninsula show abrupt marine deposits at elevations and inland distances that conventional ocean processes cannot explain. Walls of cold abyssal water crashed onto the foothills of the Andes, carrying organisms from the deep ocean floor into mountain valleys, thousands of kilometers from the impact site. The wave traveled at speeds approaching 700 kilometers per hour across open ocean. Within a day, every coastline facing the southern Pacific had been scoured. But here's where the Eltanin event becomes genuinely disturbing. The vaporized seawater didn't simply fall back into the ocean. Trillions of tons of water injected into the stratosphere, along with salt aerosols and pulverized seafloor sediment, lingered for centuries. Water vapor is itself a powerful greenhouse gas. The sudden injection of an ocean's worth of vapor into the upper atmosphere disrupted global circulation patterns at precisely the moment Earth was entering the Pleistocene Ice Age. Some climate researchers, including James Goff and colleagues writing in 2012, have argued that the Eltanin impact may have helped trigger or accelerate the onset of Northern Hemisphere glaciation. A single half-mile rock falling into the wrong patch of ocean may have nudged the entire planet into a 2 million year ice age that shaped every subsequent chapter of human evolution. What makes Eltanin particularly unsettling isn't its size. It wasn't a dinosaur killer. It was modest by impact standards. What makes it terrifying is what it demonstrated. Roughly 71% of Earth's surface is ocean. Most of that ocean is deep. The Eltanin object struck water and produced consequences more globally distributed than many land impacts of equivalent energy. A kilometer-wide asteroid landing in the mid-Pacific tomorrow would not leave a crater anyone could photograph. It would leave drowned cities on 4 continents and a stratosphere altered for the lifetimes of everyone now living. The asteroid that struck the Bellingshausen Sea 2.5 million years ago left no crater visible to the eye. It left only sediment, isotopes, and the quiet implication that the ocean is not a shield. It is an amplifier. Number 6. The Deccan traps volcanism, the catastrophe that struck the dinosaurs from below at the exact moment the sky was already falling. In 1988, geologist Vincent Cortillo at the Institut de Physique du Globe de Paris published radiometric dating that aligned one of the largest volcanic provinces in Earth's history with the precise geological boundary that ended the Cretaceous period. The Deccan traps in western India, a layered basalt plateau covering an area larger than France, had been erupting for hundreds of thousands of years before the Chicxulub asteroid arrived. But the most violent phase, the eruptive pulse that ejected the bulk of its lava and gas, occurred within a geological window indistinguishable from the impact event itself. 66 million years ago, the planet was attacked from 2 directions simultaneously. From above, by a mountain of stone moving at cosmic velocity. From below, by a wound in the crust that would not close for 1 million years. The scale of the Deccan eruption defies the language we use for volcanoes. This was not a mountain detonating. This was the continent of India, splitting open along thousands of kilometers of fissures and bleeding magma directly from the mantle. The lava flows covered approximately 580,000 square miles. In some regions, the basalt is stacked 6,500 feet thick, a vertical mile of solidified rock representing flow after flow after flow, each one large enough to bury a modern nation. The Western Ghats, the mountain range that defines India's western coastline today, is the eroded edge of this volcanic plateau. Every traveler who has stood on those cliffs has stood on the scar of an extinction. In 2015, geophysicist Mark Richards at the University of California, Berkeley proposed something that elevated the Deccan story from coincidence to causality. The seismic shockwaves released by the Chicxulub impact, traveling through the Earth's mantle at the speed of sound through rock, may have arrived in India and amplified the existing volcanism into a paroxysm. The asteroid did not just kill from the sky. It may have reached around the curve of the planet and squeezed the magma chambers of the opposite hemisphere until they ruptured. One catastrophe triggering another across 8,000 miles of solid Earth. The numbers that followed are the numbers of a planet being poisoned. The Deccan eruptions released trillions of tons of carbon dioxide into the atmosphere. They released enough sulfur dioxide to acidify global rainfall for thousands of years, dissolving the shells of marine organisms and stripping the leaves from any forest that had survived the impact winter. The climate did not simply warm or simply cool. It oscillated. Sulfate aerosols dimmed the sun and triggered cold pulses. Then they settled out, and the trapped CO2 drove temperatures upward in violent reversals. Geologists call this climate whiplash, and the term is precise. Ecosystems that adapted to cooling were broken by heat. Ecosystems that adapted to heat were broken by the next cold pulse. For any creature alive on the surface of late Cretaceous Earth, the world had become incomprehensible. Glowing red fissures stretched to the horizon across the Indian subcontinent, rivers of molten rock advancing at the pace of walking water and never stopping. The skies above the eruption zones were blackened for years at a time, blotted by ash columns that rose into the stratosphere and drifted across every latitude. Rain hissed and steamed where it fell. Lakes turned acidic. The forests that had survived the wildfires triggered by the asteroid impact now stood in a sulfurous fog that ate their leaves. What makes the Deccan traps particularly unsettling is what they reveal about Earth itself. The asteroid was an accident, an intruder from outside the system. The Deccan was not. The Deccan was the planet's own internal machinery, a flood basalt event of a type that has occurred multiple times in geological history and will occur again. Flood basalts have been linked to the Permian extinction, the Triassic-Jurassic extinction, and the end Cretaceous extinction. 3 of the worst die-offs in the fossil record correlate with the same mechanism. The Earth periodically tries to kill what lives on it. And on one particular afternoon, 66 million years ago, while the dinosaurs were still burning in the heat of an impact they could not have understood, the ground beneath the other side of the world began to open beneath them as well. Number 5. The Storegga Slide, the afternoon that drowned a country. Approximately 8,200 years ago, off the coast of what is now Norway, a section of the continental shelf the size of a small country detached from the seabed and slid into the deep Atlantic. The Storegga submarine landslide displaced an estimated 770 cubic miles of sediment, making it one of the largest known underwater landslides preserved in the geological record. The volume of material that moved was equivalent to a slab of seafloor hundreds of kilometers long, dozens of kilometers wide, and several hundred meters thick, all of it failing in minutes and cascading down the continental slope into water 2 miles deep. The ocean did what oceans do when that much material is suddenly displaced. It rose, it moved, it traveled. The resulting tsunami radiated outward across the North Atlantic at speeds approaching those of a commercial jetliner. Sediment cores from the eastern coast of Scotland, the Shetland Islands, the Faroe Islands, and the western coast of Norway have been dated to a single event horizon at approximately 6,200 BC. The deposits tell the same story everywhere they appear. Layers of marine sand, shells, and shattered organic debris driven inland and uphill by water that had no business being there. Along the Norwegian coast, wave heights have been estimated at over 80 feet. In the Shetlands, deposits sit more than 60 feet above modern sea level. In eastern Scotland, the wave traveled miles inland, up river valleys, carrying boulders, uprooted trees, and the wreckage of whatever had stood in its path. But the worst of it didn't strike a coastline. It struck a country that was already drowning. By 6,200 BC, Doggerland, the vast Mesolithic landmass that had once connected Britain to mainland Europe, had been reduced to a low-lying archipelago by thousands of years of rising post-glacial seas. Hunter-gatherer communities still lived on what remained. They fished its estuaries. They hunted its marshlands. They moved between low islands and tidal flats that rose only a few meters above the surrounding water. For generations, their world had been shrinking. They had adapted. They had retreated. They had learned to live on a homeland that grew smaller with every lifetime. Then the wall of water arrived, an 80-foot tsunami sweeping across a landscape that barely rose above sea level leaves. Nothing. There were no hills to climb. There was no high ground to reach. The wave that struck Doggerland was not a flood that receded. It was a transition, a final, violent conversion of land into seabed. The communities that had clung to those remnants disappear from the archaeological record at this horizon. Their tools, their hearths, their burial grounds, their dead, all of it now lies beneath the cold floor of the southern North Sea, scattered and buried under marine sediment that has been accumulating for 8,000 years. What makes the Storegga slide particularly unsettling is what preceded it. Nothing. No earthquake on land. No tremor a coastal fisher could have felt. No warning visible from any shore. Submarine landslides occur in silence. The ocean floor simply gives way, and minutes later, walls of water are crossing entire seas. The people of Doggerland, of Mesolithic Scotland, of the Norwegian coast, possessed no framework for understanding what was happening to them. There was no language for a sea that rose 80 feet in minutes and raced inland carrying boulders the size of houses. There was only the water and what the water did. The Norwegian continental margin remains geologically active. Sediment continues to accumulate on the same slopes that failed 8,000 years ago. The conditions that produced the Storegga slide have not disappeared. They have simply been waiting. The Mesolithic communities erased by the wave numbered perhaps in the thousands. The modern populations living along the same coastlines, in cities built directly atop the tsunami's ancient deposits, number in the tens of millions. They have warning systems and seismic networks the people of Doggerland could not have imagined. Whether any of it would matter in the minutes between collapse and arrival is a question the seabed has not yet answered. Number 4. The Lake Agassiz outburst flood, when a single lake rewrote the climate of a continent. The Storegga wave killed a population. Lake Agassiz killed a climate. The two events occurred within decades of each other, both tied to the dying convulsions of the last ice age, both delivered without warning to communities that had no framework for understanding the forces aligned against them. But where Storegga drowned a coastline, Agassiz drowned a hemisphere's atmospheric balance. Approximately 8,200 years ago, in what is now central Canada, an ice dam holding back one of the largest freshwater bodies the planet has ever produced finally gave way. Lake Agassiz was not a lake in any modern sense of the word. It was an inland sea, larger than all 5 modern Great Lakes combined, fed for thousands of years by the meltwater of the retreating Laurentide ice sheet. It stretched across what is now Manitoba, Ontario, Saskatchewan, Minnesota, and North Dakota. Its volume was incomprehensible. When the dam holding it back collapsed, an estimated 38,000 cubic miles of freshwater drained into Hudson Bay, and from there into the North Atlantic over a period of months. The numbers are not the kind of numbers human beings are equipped to process. 38,000 cubic miles of water released in geological seconds. Enough freshwater to raise global sea levels by 1 to 4 feet almost overnight in geological terms. Enough fresh water to permanently reshape the salinity of the North Atlantic. The physical evidence of the drainage is still legible in the landscape. Icy, gray-blue tidal currents carved canyons through bedrock that had stood unchanged for hundreds of millions of years. Grinding ice slabs the size of skyscrapers tore through river valleys, scouring the underlying stone, gouging channels that geologists still trace from satellite imagery. The Hudson Strait shows erosion patterns consistent with discharge rates that exceed anything in modern hydrology. The flow ripped sediment from the seafloor and deposited it in fans across the Labrador Shelf. Even the bedrock recorded the violence of what passed over it. But here's where the standard explanation falls apart into something far more disturbing. The flood itself was not the catastrophe. The flood was the trigger. When 38,000 cubic miles of fresh water poured into the North Atlantic, it did exactly what Wallace Broker's models had predicted decades later that such an influx would do. It shut down the Atlantic thermohaline circulation. The vast conveyor of warm, salty water that carries tropical heat northward and keeps Europe habitable simply stopped. The salinity required to drive the sinking of cold, dense water at high latitudes was diluted past the threshold. The engine quit. Europe plunged into a mini ice age. Temperatures across the North Atlantic region dropped by several degrees Celsius within decades. In some regions, winter conditions intensified by more than 5 degrees. The cold persisted for over a century, possibly closer to 2. The growing seasons that early Neolithic communities had built their existence around contracted. Crops that had been viable became marginal. Pastoral lands that had supported herds for generations could no longer carry them. Glaciers in Scandinavia, which had been retreating for thousands of years, paused and in some valleys advanced again. What makes the Lake Agassiz outburst particularly terrifying is the speed of the cause and the duration of the consequence. The lake drained in months. The climate it broke remained broken for over a century. A single geological event lasting less than a year reshaped the conditions of human existence across 3 continents for 5 or 6 generations. The farmers who planted seeds in the fall of one year and harvested smaller crops the next had no way of knowing that an ice dam on the other side of the world had failed. They experienced the consequence as inexplicable. Their gods had turned. Their fields had betrayed them. The weather had become an enemy. The truly disturbing aspect is the fragility the event revealed. The North Atlantic circulation is not a permanent feature of the planet. It is a balance, maintained by salinity, temperature, and density gradients that can be disrupted by a single, sufficiently large pulse of freshwater. The lake that broke it 8,200 years ago no longer exists, but the mechanism does. The Greenland ice sheet contains volumes of freshwater comparable to what Lake Agassiz released. It is melting now, and the engine that keeps Europe warm runs on a margin thinner than the ice that once held back a vanished sea. Number 3. The Younger Dryas impact when the comet killed the Ice Age world. In 2007, nuclear physicist Richard Firestone and a team of 25 researchers published a paper in the Proceedings of the National Academy of Sciences proposing something extraordinary. Approximately 12,800 years ago, at the precise moment the Earth was finally emerging from the last ice age, something struck. A comet or asteroid, likely fragmenting during atmospheric entry, detonated in a series of airbursts over the Laurentide ice sheet covering North America. The resulting cascade sent the planet plunging back into glacial conditions for over 1,000 years. This period is called the Younger Dryas, and its onset represents one of the most abrupt climate reversals in the geological record. The evidence is embedded in a thin, dark geological layer found at over 50 sites across 4 continents. This Younger Dryas boundary layer, sometimes called the black mat, contains materials that should not exist together in ordinary sediment. Nanodiamonds, microscopic carbon structures that form only under the extreme pressures and temperatures of cosmic impact. Glassy melt spherules, tiny beads created when rock vaporizes and resolidifies midair. Elevated concentrations of platinum, an element rare on Earth's surface, but common in extraterrestrial bodies. And across vast stretches of North America, a carbon-rich layer of soot and charcoal consistent with continent-scale wildfires. The numbers are staggering. The platinum spike identified in Greenland ice cores corresponds precisely to the Younger Dryas boundary. Sediment samples from sites in South Carolina, Arizona, Pennsylvania, and as far away as Syria contain the same impact-related materials in the same narrow horizon. Whatever happened 12,800 years ago, it happened everywhere at once. The black mat itself blankets archaeological sites across the American continent, sealing the world that existed before beneath a layer of carbonized debris. But here's where the discovery becomes genuinely disturbing. The black mat doesn't just mark a climate event. It marks the end of an entire human world. The Clovis culture, one of the earliest well-documented human populations in North America, vanishes from the archaeological record precisely at the Younger Dryas boundary. Their distinctive fluted spear points, found across the continent in earlier sediment layers in remarkable abundance, simply stop appearing above the black mat. The people who made them, hunters who had spread across an entire continent, who had developed a sophisticated and recognizable material culture, are gone. Not migrated, not transformed, gone. Simultaneously, the megafauna they hunted disappeared. Mammoths, mastodons, saber-toothed cats, giant ground sloths, American camels, American horses, dire wolves. Species that had survived multiple glacial cycles, that had endured hundreds of thousands of years of climatic stress, vanished within a window narrow enough to be invisible in geological time. Approximately 35 genera of large mammals extinct in the Americas during or immediately after the Younger Dryas onset. The bones lie beneath the black mat. Above it, nothing. The climate data confirms the violence. Greenland ice cores show temperatures in the North Atlantic region collapsed by approximately 7 degrees Celsius within decades. The warming that should have continued for thousands of years simply stopped, as if someone had reached into the planet's thermostat and twisted it back. Ice sheets stabilized. Glaciers advanced. The world that had been thawing froze again and stayed frozen for over a millennium. What makes the Younger Dryas impact hypothesis particularly unsettling is the visual record reconstructed from the evidence. Multiple fireballs streaking the sky over a continent. Glassy melt spherules raining onto frozen plains. Forests across thousands of kilometers ignited simultaneously, burning until there was nothing left to burn. The carbon signature in the black mat suggests wildfires on a scale that has no modern analog. An entire continent's worth of vegetation reduced to charcoal in a season. The debate over the cause continues. Some researchers argue the nanodiamonds and spherules have alternative explanations. Some attribute the megafaunal extinction to human overhunting. Some attribute the climate reversal to meltwater disruption of ocean currents. But the coincidence resists dismissal. At precisely 12,800 years ago, temperatures collapsed. Continent-wide fires erupted. A sophisticated human culture disappeared, and dozens of species went extinct simultaneously. Whatever pulled the trigger was pulled. If the impact hypothesis is correct, it means that the trajectory of human civilization in the Americas was severed by an object from space. The Clovis people who had colonized an entire hemisphere were erased. Whatever they were becoming, whatever cities or cultures might have grown from their expansion, none of it happened. The survivors started over in a frozen world surrounded by the bones of animals that would never walk the earth again. Number 2. The Toba supervolcano eruption and humanity's near extinction. Approximately 74,000 years ago, on the island of Sumatra in what is now Indonesia, the Earth detonated. The Toba supervolcano expelled an estimated 670 cubic miles of magma in a single eruptive sequence, an event that ranks as the most violent volcanic episode of the last 2 million years. To grasp the magnitude requires abandoning ordinary comparisons. The 1980 eruption of Mount St. Helens ejected roughly a quarter of a cubic mile of material. Toba expelled nearly 3,000 times that volume. The eruption blasted a column of ash and pulverized rock 18 miles into the stratosphere, punching through the layer of atmosphere where weather occurs and depositing its payload directly into the global circulation system above it. The hole it left in the planet remains visible from orbit. The caldera that formed when the magma chamber emptied and the overlying crust collapsed stretches 62 miles long. Lake Toba now fills the scar, the largest volcanic lake on Earth, occupying a wound so vast that entire towns sit comfortably along its shoreline. The volume of rock that simply ceased to exist as a mountain and reappeared as ash in the upper atmosphere is incomprehensible at human scale. An island-sized fragment of the Earth's surface was converted to airborne debris in a matter of days. That debris went everywhere. Ash layers from the Toba eruption have been identified in sediment cores across the Indian Ocean, in soil deposits across the Indian subcontinent reaching thicknesses of 6 inches and more, in the South China Sea, and in lake sediments in eastern Africa, nearly 4,500 miles from the source. For weeks following the eruption, gray snow fell across continents. Vegetation suffocated under accumulated ash. Water sources turned to abrasive slurry. The atmospheric injection of sulfur dioxide formed sulfate aerosols that scattered incoming sunlight and tinted the upper sky a deep, persistent red. Across what would have been the entire daytime hemisphere, the sun was wrong. Then the cold arrived. Climate models and proxy data converge on the same conclusion. Toba triggered a global volcanic winter, lasting between 6 and 10 years, with peak temperature drops of up to 18 degrees Fahrenheit in some regions. Growing seasons did not shorten. They stopped. The tropical belts that had supported the highest densities of early human populations contracted toward the equator and thinned. Forests died back into grasslands. Grasslands died back into dust. But here's where the eruption stops being a geological event and becomes a human one. In 1998, anthropologist Stanley Ambrose at the University of Illinois published a paper that connected Toba to a puzzle geneticists had been circling for years. Human genetic diversity is conspicuously low, astonishingly low. A single troop of chimpanzees in Central Africa contains more genetic variation than the entire human population of 8 billion people. Something, at some point in our deep past, compressed our ancestors into an extraordinarily small breeding population. The signature of that compression is written into every cell of every human alive. Ambrose proposed Toba as the cause. Subsequent genetic analyses suggest the global human breeding population at the time of the eruption may have collapsed to between 3,000 and 10,000 individuals. Not 3,000 in a single valley. Not 10,000 in one favored refuge. 3,000 to 10,000 total. Every human being who has ever lived since, every farmer, every emperor, every architect of every civilization that has risen and fallen across the surface of this planet descends from a population small enough to fit inside a single sports stadium with seats to spare. The debate over Toba's precise role continues. Some archaeological sites in India and southern Africa show evidence of human occupation continuing through the eruption layer without obvious collapse. Other researchers argue the genetic bottleneck predates Toba or postdates it. The questions are unresolved. But what is not in dispute is the eruption itself, its magnitude, and the fact that something during this window in deep prehistory reduced our species to a population that could be erased by a single bad winter. Consider what was actually at stake if the eruption had been marginally larger, if the winds had carried the ash differently, if those few thousand survivors scattered across the cooling continents had been slightly less resourceful, slightly less lucky, slightly less fortunate in the timing of a single birth, every human achievement of the subsequent 74,000 years would not exist. No language we speak, no story we remember, no name we carry. The entire trajectory of our species balanced on whether a handful of cold, hungry people could outlast a sky that had turned the color of blood. They did. Barely. And the world that followed inherited their fragility, along with their survival. Number 1. The Chicxulub asteroid impact, and the day the sky caught fire. 66 million years ago, an object between 6 and 9 miles wide crossed the orbit of Earth and did not miss. It struck the shallow waters off what is now the Yucatan Peninsula at approximately 45,000 miles per hour. The impact lasted less than a second. The consequences lasted longer than every human civilization combined, and they are still being measured today. In 1980, physicist Luis Alvarez and his son, geologist Walter Alvarez, at the University of California, Berkeley, published a paper in Science proposing that a thin global layer of iridium-rich clay marking the end of the Cretaceous period was the signature of an asteroid impact. The scientific community resisted the hypothesis for over a decade. Then, in 1991, a buried structure beneath the Gulf of Mexico, originally identified by oil company geophysicists in the 1970s, was confirmed as the impact crater. It measured 100 miles across. It had been hiding under limestone and seawater for tens of millions of years. The Alvarez hypothesis was no longer a hypothesis. The killer had been found. The numbers defy comprehension. The energy released at the moment of impact has been estimated at the equivalent of 10 billion Hiroshima bombs. The asteroid struck with such velocity that it punched through the atmosphere faster than the air could move out of its way, creating a vacuum corridor behind it before the surrounding atmosphere collapsed inward in a shockwave that flattened forests across the Americas. The flash of the impact was visible from space, a blinding white star blooming on the surface of the Earth, brighter than the sun for an instant, then darkening to a 100-mile-wide crater glowing molten orange. A black mushroom cloud rose to the edge of space, lifting trillions of tons of vaporized rock into orbit. Mega-tsunamis surged outward across the Gulf of Mexico, reaching estimated heights of 1,000 feet near the impact site. Coastal forests across what would become Texas, Cuba, and Florida were stripped to bedrock. Sediment cores drilled from the Gulf seafloor show chaotic deposits of mixed marine and terrestrial debris, the geological signature of a wave that didn't care what it carried. But here's where the destruction becomes truly incomprehensible. The crater and the wave were not what killed the dinosaurs. What killed them was the sky. The impact lifted billions of tons of pulverized rock into ballistic trajectories. Most of that debris did not escape Earth's gravity. It came back down. Across hours, every fragment that had been hurled upward re-entered the atmosphere, and each one heated to incandescence on the way back through. The cumulative effect was an atmosphere that became, briefly, an oven. Surface temperatures across vast regions of the globe rose to an estimated 500 degrees Fahrenheit. Anything exposed to open sky cooked where it stood. Forests ignited spontaneously on continents thousands of miles from the impact site. Charcoal layers from this exact moment have been identified in sedimentary records across North America, Europe, and Asia. The world burned in a single afternoon. What followed was darkness. Soot from global wildfires and dust from the impact blocked sunlight for months, perhaps years. Photosynthesis collapsed. Surface temperatures plummeted from oven hot to freezing within weeks. The food web disintegrated from the bottom up. Plants died. The animals that ate plants died. The animals that ate those animals died. By the time the skies cleared, 75% of all species on Earth were gone, including every non-avian dinosaur lineage that had dominated the planet for 165 million years. What makes the Chicxulub impact the most disturbing entry on this list is not its scale, though its scale exceeds every other event we have described. It is its randomness. The asteroid that ended the Mesozoic era was one object on one trajectory at one moment in cosmic time. A difference of a few minutes in its arrival would have placed the impact in the deep Pacific or the open Atlantic, with consequences entirely different from those that shaped the world we inherited. Mammals inherited the Earth because a rock arrived on schedule, and the sky has not been cleared since. Objects of similar size continue to cross Earth's orbit. Astronomers have cataloged thousands of near-Earth asteroids and identified the trajectories of the largest. They have not identified all of them. The civilizations we have built, the cities we inhabit, the species we have become. All of it exists in the brief interval between impacts. The crater off the Yucatan coast is still there, buried under limestone and water, a 100-mile scar on a planet that has been struck before and will be struck again. If you want to see more videos like this, click the video on screen now and make sure to subscribe.